Thank you. So thank you for the invitation, and this chance to speak here. So let me first explain the statements of the result, and then give some way of understanding it instead of going to to the technical details. I think, yeah, I think that would be for the benefit of most people. So, so this is a joy work with Siu-Chang Lau, Leon, Lee, and Kev and Chen. And also it's supported by the research fund from the Hong Kong government. All right, so we are studying floor theory. When you have a group actions. G is a compact group. So let's try to look at some example first. For example, let's say the group is a torus. Okay. So in this case, when we study mirror symmetry from XYZ perspective, and this is related to also the conjecture by Telemans of how to understand equivariant floor theory, equivariant mirror symmetry. So if you have no group actions, then you look at the A side for the symplectic manifold, and then you try to understand the mirror manifold. In this case, Y is we realize as the moduli space of Lagrangians with a flat U1 connections. So, just here. So L will be a Lagrangians in here, and this is a flat U1 bundle or U1 connections on L. Okay, and that you think about as a mirror manifold. Traditionally, we should look at L to be the Lagrangian tori to be the SYC mirror. But this kind of family floor transform or the mirror transform, you can do it for interchanging the Lagrangian geometry to the complex geometry. You can do for any Lagrangian, not necessary. Torus, is this it? Okay. So what if you have a torus action first? That will be easier to describe. Okay. So if you have a torus action, act on Y, and then if you have a Lagrangian, which is also T invariant Lagrangian, okay, that will first imply that this one, the value at point is constant. So you just denote this. So this is a constant function. It's constant in here, just a particular value. Okay. And the second statement is if any deformations of L as a Lagrangian is again T invariant up to Hamiltonian deformation. So that means that the whole component of the moduli space all consists of Hamiltonian, all consists of T invariant Lagrangians. Okay. Each of them is a fixed moment value. Okay. So then we describe, so in general, because Y typically is not like Calabi-Yau. Because if I compare Calabi-Yau, you really cannot have any continuous group actions. Well, non-compare you can, but So in general, if it's not Calabi-Yau or even Calabi-Yau non-compact case, besides this space Y check, which is all this Lagrangian reflect connections, and it also will come with a superpotential functions. And then in the case of Calabi-Yau, that function is just constant. And this is the count of mass of index 2, this in Y bounding L. So let's just choose a look at an example. So let's say if you look at Y is C2, so this is just this. Okay, C2. Okay. So so if I draw the as a moment map value of T2 actions, let's say, then the image is just this. The moment map is just 1/2 of Z1 square and Z2 square. 1/2 of Z1 square, 1/2 Z2 square. Just like this. Okay. And the fiber over each point will be a Lagrangian tori, and a fiber over this point will be just a circle and so on. Okay. So if you look at this, these are T very Lagrangians, and then in this case, they will bound two mass of two disks. One is bounding this one. The other one may be bounding this one. It's the same disk that was this a standard disk in R2. Sorry? Yes. But I'm just doing it more. Yeah. So I didn't even write down a definition. Just say it like that. Yeah. So the thing is that either you know it or that would be the best. I think. All right. So let's say if you instead of looking at this, if you look at T1, for example, T1. So this is the moment map, just sum of that, and then the map will be just mapping to out. So map to out. Okay. So let's look at smaller torus, for example. Okay. What we know in this case is so in this case the mirror in this case will be C star square, and then the function W check will be Z1 plus Z2 to C. Okay. So we want to understand the geometry of upstairs and the geometry of downstairs. So here is an example that in general, if you have this, then this space will also come with a map to the following, which is the dual torus cross T star. Okay, this is just both in the sense of dual. So if you have one of this, then this map, let's just call it pi, will send L to this moment map value. And then the flat connections on this, then we'll be looking at the holonomy of the flat connections along all the circle in the original torus actions. Okay. So that would be an element in the dual torus. Okay. So call this element pi. Okay. So in this particular case, the map is just Z1 times Z2 or 2C. Okay, maybe I should write as mu here. Yeah. So 2C star, sorry. So I write this one as a complexified torus. Okay, this R cross S1 becomes C star. Okay. So in this particular example, you see that this you can think of as a mirror statement. Okay. If you choose a particular value, moment map value, lambda here, and then you do the symplectic quotient by lambda of T1. Okay, of course this is just a CP1 in this case, where the symplectic form, the size is roughly e to the lambda, so on. Okay. And then you can read off this quotient from the other side, because the mirror of this one, we all know that is given by C star with a potential function given by z plus 1 over z. In fact, lambda over z, e to the lambda over z. Okay. Which is exactly the same as the fiber over this element here. So if I write the element lambda to an element in C star, it looks like e to the lambda. It is exponential of that one. Yeah. And this is exactly the fiber over this. The fiber over the lambda is a copy of C star here, and then the restriction of the function is given by that. Okay. So therefore, this is so-called a Hori-Rafa mirror. So the prediction is the following. If in general, you have a torus action acting on Y with a moment map T star, okay, and so you look at the modular space of this with the functions Y counting disk, and so this is for Y. Okay, the action will turn into a map to the complexify this, and the map again is given by mu of L and the holonomy of the flat connections along the orbits of the T actions. Okay. And the conjecture, Hori-Rafa statement, and the Telemann's conjecture in the abelian case for G equal to torus case should be saying that in good cases, under some assumptions, like final type conditions, that if then the mirror of Y, if you do a quotient of that at the value lambda here, then it's mirror, two-dimensional mirror symmetry to the pi inverse of this value lambda here, or maybe e to the lambda, and let me just denote it as y check lambda, and then with the potential function restrict to this fiber. Okay. So in the case when the toric case, that is a Hori-Rafa mirror. And we also know that Hori-Rafa mirror is not the mirror. There will be correction, so I will mention that in a second. So that will be further correction for this statement, in fact. Okay. Now, but in non-abelian case, so I describe the correction later in the talk. So, so now this is G actions acting on Y. And then if you look at the Catan's subalgebra, then you do the projection to T star, then that's the moment map for the T actions. Okay, so you can reduce from the G to the T questions. Okay, well, and we'll be still looking at the same mirror. So these are again Lagrangian, which are T invariant Lagrangian, not G invariant, just T invariant Lagrangians in Y. Okay. It also have the same W check here. Okay. And want to see, so you because of the T action, so you still have this map to TC check. But where is the G action data coming in? Okay, and the claim is that exists. From this data, you can construct the following data. Is called the C track, the CG the Y, maybe CGY, maybe mapping to CGY, which is a complex Lagrangian inside this space spectrum of the homology, equivariant homology of G of the loop space of G. Okay, so these are called the BFM space by Pisarkonikov, Frankelberg, and Mikovic of the Lang-Lang group, and sometimes also called the Coulomb branch of the pure n equal to 4 gauge theory. Branch. Okay. So let me say the statement for you, the result here. So so the first statement is a result with trend. That in this case, that suppose so I'm just going to call this L, this data, call it L. So instead of writing this as L lambda, just write it as L bar, meaning L decorated with the flat connections. Okay. Suppose this one is not equal to 0, then this map, let's see just a second, then this pi of L bar, which is sitting inside T C check, in fact, lie inside the center of the Lang-Lang group. Okay. So, sorry? Pi is this map. This map. That map. Pi. Okay. That will already imply, in the case of SU2, that it lies inside the Coulomb branch. So in general, then we need to do it for every root. Okay. Okay, so the main difference here is the following. So why I did this assumption. So this one is not equal to 0, is equivalent to dW at the value L bar. L bar is a critical point of the W check if only mass of 2 disks contribute to the curve, contribute to this the floor differential. So if in these good cases, like some final type assumptions, if that is the case, then you don't need the assumption because this is exactly what we want. Yeah. Yeah. You have to have a T equivariant actions. Yeah. 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 So okay. So what do you want? So y to be c star to the n? Yes. Yes. Yeah. So for example, you got Tn actions, then y check is against c star to the n, right? and then the map pi will be identity. Yeah, but in that case, these are all 0 because y just move away. It's 0. It's 0. Yeah, yeah. So, sorry. Yeah, yeah, yeah. Yeah. Basically, I assume yeah. So let me just tell you what you need here, and then how do you think about this problem? Okay. Yeah, yeah. Let me explain that now. Yeah. So then that's all this. Why don't I describe the second statement and then come back to that? Okay. So the other statement is the following. This is a torus action. Okay. So this is a joint work with Lau, myself, and Li. Okay. So so this is a torus action case. The statement is, first of all, if you fix a value lambda here, okay, then the mu inverse of lambda will be Lagrangian inside the y and then y quotient by torus. Is generally true. Okay. So then if you look at T invariant Lagrangian here, okay, because the T invariant Lagrangian, let's assume that the moment value of the Lagrangian is lambda, okay, then it will descend to a Lagrangian in here. Let's just call it TL bar, let's say, descend to here, okay. And so you can also really come from a Lagrangian here, call it L pi, for example. And these are related by Lagrangian correspondence. These are related by, so let me say the Lagrangian correspondence second. So the statement is the following. You can look at the function W. Mu inverse lambda is a subset in Y, but it projects to here. Okay, so mu inverse of lambda is a subset in Y, and then you get symplectic quotient to my, and this is Y quotient by T. So you look at the map to this and that. Yeah. So now this becomes a Lagrangian here. The claim is if the Hori-Rafa mirror work, that would mean that if you try to compute a W on here and the W on the downstairs should be the same. That was what Hori-Rafa mirror said. Erase that one, okay? Because they're just saying that the mirror is just restrict to the fiber and then look at the same W, okay? So that would meaning that corresponding to the same W for L and whether equal to this one, okay? And that would be, if that is true, that will give you the Hori-Rafa mirror, say that the quotient is the fiber. And the statement is that this will be different by the contribution from this Lagrangian in the product, okay? And this is a further correction. So this is, of course, because we have to compute the floor theory here, this is under the assumption that this Lagrangian is really unobstructed, yeah. So assuming this Lagrangian is really unobstructed. So you can define the W obstructed. Yeah. So for example, if you look at Hilbert surface F2, then in that case, you already know that the Hori-Rafa mirror is only approximations, and then this tells you exactly what that is. Okay. So let me put this in perspective and answer your questions. Yeah. Yes. Yes. So this one, you have to do Lagrangian trimodule constructions because that this one is because really have to use this one at the same time. So you are involving self composition of Lagrangian correspondence, which was discussed in the paper by Fukaya about Lagrangian trimodule. So we have to use based on that technology. And what we further need is the following: we need to do, because that is built on a situation where the composition is transverse composition. This is a clean composition. It's not a transverse composition. The second situation is we have to adopt it to the G equivariant setting. So no, I'm saying this. Then the second statement is that you need to do it in an equivariant setting by looking at finite dimensional Borel constructions. And so you have to do it on the whole Borel, finite dimensional Borel approximations. That was wrong. It's not. You have to have a T here. Otherwise, not true. Yeah. It's like the equivalent cohomology is really the cohomology of the quotients. Yeah. And that's one more. So you have to do this too, and also you have to yeah. So basically, you have to adopt it to the group action. So therefore, you have to do the you have to build it on the whole Borel structure too. Yeah. So that was a lot of things to check basically, yeah. And also the clean setting. Yeah. Okay, and okay. So let me explain the structure which are behind is the following. So let me start from something very basic. So if you are on a one-dimensional theory, then you may look at a one-dimensional space mapping to a Riemannian manifold. And then if you quantize, then you get a Hilbert space. In this case, just a cohomology of M. So you treat it as a Hilbert space, a finite dimensional Hilbert space if it's finite dimensional. Okay. And returns theory. Then if you're in a two-dimensional, like a string theory, you get an A and B model. Then you look at this mapping to some Conan manifold, for example. You may have a potential function and so on. Then you may also want to couple, because you have a string, so you can have a boundary conditions by saying that the boundary, which is a one-dimensional space, mapping to some subspace inside Y, you have to try to preserve at least as much supersymmetry as possible, meaning n equal to 1 supersymmetry on boundary. So on the boundary, you can also couple with 1D theory along L. So meaning that for each point you have a Riemannian manifold and so on. But well, after you quantize, that just means that you have a Hermitian vector bundle over L. Okay, so you want to have a meaning that you get a Hermitian vector bundle over L. Okay, and now depending on the A and B model, and the A model, then you assume L is Lagrangian, E is flat. Or B model, you assume L is holomorphic and E is holomorphic. Okay. Now, if you are in 3 dimensions, if you just do the naive generalization, in this case, let me say one more thing. So say Y is really a symplectic quotient of a point. Okay. Then you should think that a subspace in here, now we are saying a model. A subspace in here, Lagrangian subspace will be just a usual quotient of a point sitting inside a symplectic quotient, for example. Okay, and then now you couple with a Hermitian vector bundle that is the same as saying that this is just a point. This is saying that E is a representation of G. Okay, unitary representations. Okay, so you can look at this as a boundary condition in a stacky setting. Okay, so now if you are in 3D, then we may look at free manifold mapping to, let's say, a hyperkähler manifold with a metric and omega ijk and so on, and complex structure ijk if you like. Okay, and let's say you pick a complex structure, so it's a j and then omega j and then omega j, so omega I minus I omega k. One. So this is so meaning that you're only looking at the holomorphic symplectic structure. And in this case, the boundary conditions will be some submanifold on X together with a family of 2D TKFT and equal to 2. So for example, we will assume then that this is just a family of Kähler manifold. So just look at Y is really a Kähler manifold with a holomorphic map here. Oh, map, okay. And this is a complex Lagrangian, omega J Lagrangian. Okay, here's the holomorphic map. So for example, you can view this in two different ways. So given this X, you get this complex Lagrangian. This is Y, J, Y, omega Y. Okay, let's for simplicity, let's assume that this is just a fiber bundle, topologically fiber bundle. I mean, the map is smooth. Okay, no single fiber in this case. So you can view in the two. If you're thinking about 2D theory in the A side, okay, then that you get that for each C, you will be looking at the Fukaya category of the fiber, and then omega restrict to the fiber. Okay, but then because the omega Y is a globally defined class, so this class is really constant when you vary C. The class is really constant class. But by looking at under diffeomorphism of identifying various fibers, it's locally constant class. X is a hyperkähler manifold, which we are thinking about as a target of a 3D theory. Now we want to look at the boundary conditions, which consists of a subspace and some family of 2D TQFT. So here is a particular geometric setting. So assuming that you have a Kähler manifold, have a holomorphic map, the image is a complex Lagrangian. So in this case, you get a family of 2D TKFT as a family of a Kähler manifold, it's parameterized. Yeah. Yes, we will do that too. Yeah. Yes. So in this case, if you're looking at this two-dimensional family, because Kähler manifold can define either A or B model. If you're thinking about A model, then you will parameterize a. So because the Fukaya category is invariant under default if you fix the class. So this is giving you a locally constant family of category parameterized by C. Okay, of course, I do not know how to do it when the fiber can be very singular, but presumably that you get Schubert or something. Okay, which I don't know. And same. If you do on a B side, this is a holomorphic family of category primary choice by C. Okay, so you can think about it as this is a DC linear category, if you like. So the B side is much easier to describe. And the setting that we are interested is the following. So now Y, the hyperkähler manifold in our situation is just a point, hyperkähler quotient by G. And this is A side. Okay, I should mention that I'm not defining the whole theory, like I'm not defining floor theory. I'm just looking at for some particular object that we can understand what is happening, rather than defining the whole, like what is a Fukaya category or that. Okay, so just look at a particular object in this setting, and then in this case, so-called the 3D mirror symmetry, which says that this subject is related to another hyperkähler manifold. In this case, this is quite easy to describe. This is just a cotangent bundle of C star. Sorry, this is when this is a torus. Then this one's cotangent bundle of T check C. Okay. Or if you, or more generally, if X is a star quotient by G, then it's supposed to be this one is this BFM space spectrum of homology of the loop group. And if the G is a abelian group, that's the same space here. So that's why what we want is the following. So if you're given an object here, okay, meaning that I have a G here, maybe I write it here. Okay, so our object here will come from a complex Lagrangian. For example, this is just a point symplectic quotient by G, and then you get a family over here. Okay, so this is A side. Okay. So that means that, yeah, that's like a 2D case. This is the same as saying that you have a Hamiltonian symmetry here. Okay. Now the aim is to construct from this. You want to see that the mirror space. You want to use the mirror space to construct an object here. So you want to construct. I'm going to just call it CYG. Okay. So that would be consist of a complex Lagrangian inside here, together with a family over that. Okay. And then the next thing is you look at two objects. One. Just yeah. Okay, so this means the following. Let's just assume G is a T, S1, okay? So I would be thinking about the following, more precisely, is, so say G is, let's say S1, okay? So we're looking at cotangent bundle of CP infinity. Of course, when I say CP infinity, I should do it for all n, okay? And then let n go to infinity. And that would be having a Lagrangian, which is CP infinity, and then this is like the X, and this is like the Lagrangians of space here. And so, for example, if you look at X to be the same as this, as Y, as you just mentioned, okay, and then you can look at Lagrangian here, which is CP infinity. So this is like point quotient, hyperkähler quotient, symplectic quotient, usual quotient. Yeah, so that would be, that is the case that we are looking at in the Abelian case. We are exactly doing this model, basically. This. Oh, sorry. This is supposed to be in. Let's just call this BFM. That's the notation. G hat. So BFM G hat. So 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 in the case of S1, is this cotangent map of C star. Now you see the C star. So in fact, we already have that. I told you already here that yeah. I'm telling you now. Yeah. So if you have S1 acting on Y, okay. So the mirror space will come with a function W check, and then with this function pi to C star. This is the same star there. Okay. This is the C star inside the cotangent bundle of C star. Okay. But this is not the Lagrangian. So S1 act on A side. So that's why this one so what we need is to describe this as a family over cotangent bundle of CP infinity. Let's just call this space of YC star. Okay, and that sits inside the cotangent bundle of CP infinity. Okay, and then the Lagrangian correspondence will give you inside here CP infinity. And then the Lagrangian fiber, this will be Lagrangian of S1 in here, and that would be the Lagrangian in this case. Yeah, so that is the equivariant theory we need to do for all. Yeah. Then, yeah. So at the moment, the constraint I just imposed, because I'm not a physicist, you may tell me more. It's just that you're looking at complex Lagrangians, and it's a family of, it's a Kähler manifold. For the boundary condition, yeah. Anomaly cancellation, yeah. I cannot do those calculations. This should give you the right answer, but I just do not know how to do those calculations. Yeah. Yeah, I mean, his question is more, normally is in 3D, in fact. Yeah, that is further calculation, I suppose. But anyway, I cannot answer those physics questions. All right, so let me continue to tell you what is this one. So you get a map pi to here, okay? Then what you do is you want to get a Lagrangian here. The way to do it is the following. Okay? You basically want to still look at the graph of dw, basically, okay? So the thing is that the graph of dw will be a Lagrangian inside the cotangent bundle of y check, right? This is a Lagrangian in here. And the pi, if you look at the graph of pi, that will give you a Lagrangian inside the cotangent bundle of y check cross the cotangent bundle of C star. Okay, and then you use this as a Lagrangian correspondence to go from this Lagrangian to a Lagrangian in here. And that is our Lagrangian. This would be Ty, because it may not be transferred, so that's why in general this may not be identity if you have everything transverse. Or this, if everything is transverse intersections, then this is just this is equal. In general, you get. Yeah, this is just Lagrangian correspondence to get this element. So this is, you use this, you pull this there, intersect this, and push forward. Yeah, it's a holomorphic. Yeah, it's a holomorphic Lagrangian correspondence on the B side. Holomorphic. I mean, yeah, intersect for sure. So it's a holomorphic symplectic thing. I mean, the A side is just real Lagrangian correspondence. So yeah, and that gives you this element here. Okay, that is this element in the case of G. Okay, now you want to now, as I mentioned, then the following. So this gives you one element. Let's just look at G equal to T case. Let's continue G equal to S1 case. Continue. Okay, so given Y to this, Hamiltonian, okay, so this is A side, and I'm just, for simplicity, writing this way. And then on this side, you get Y check, W check over C star inside cotangent bundle of C star. And then you go from this to do this construction to get C. T, Y here, I think. Yeah, okay, so basically these two are the same. You can think about this. This is the Hamiltonian deformation of this to that one. So not really different. Now, so this is one object correspondence in here. So this is the object in star quotient by S1. The other is the object in here. Let's look at another object. So the other object is S1 acting on a point. That's acting on a point. But then you can still have the moment map value. Let's say the value is called lambda. Okay, so this is, when I say this is mostly non-degenerate case. This is a completely degenerate. The whole action is very trivial. Okay, so in this case, this object in this case is inside cotangent bundle of C star. Instead of C star, which is really the Lagrangian, is just cotangent fiber at lambda. Just a fiber. Instead of the base, this is a fiber. And upstairs is also the same. It's an identity in this case. You do the same reasoning, but except this is a constant trivial action. So you just concentrate on this fiber. You need some argument. All right. So now the question is, the home of this one should be the home of that one. Okay. So the moment map value will be just 1 point, right? Because the whole space is just 1 point. The moment map value of that, I call it lambda. It's just some element, I call it lambda. It's an image of 1 point. It's still a point. Yeah, this is a boundary condition, yeah. Yeah, the data, yeah, the lambda describe the boundary conditions, yeah. So now you want to think that if you compute a home on this side, so this is really, one of them is S1 acting on Y, the other one is S1 acting on a point with moment map value lambda. Now this is on the A side, on the 3D theory, and then you ask whether this is related to the home on the B side. Now one of them is this Lagrangian. Let me just, for simplicity, just write as Y check to C and W check to C star. So this is cotangent bundle of C star. Okay, so this one is something like here. And then the other element will be cotangent fiber of lambda of this. So that would be this fiber. Okay, so this is one object here, this is the other object. So whatever definition of the home is an intersection theory. Is an intersection of two Lagrangians inside. So of course in the right hand side, so it's easy to see what the intersection. They only intersect at a point basically. Okay, so the right hand side is just the intersection of a point. If you look at it as a B theory, that would be just whatever theory, derived category, but maybe with a Y check at the point and W check along that point. Or matrix factorization, whatever. And this one is, so you can think about that this is an object in, this is an object, you can think about this as Y on SY to this one quotient by S1, and this one also go to point quotient by this one quotient by S1 inside the point hyperkähler quotient by S1 basically. And you give it a thought, and then this is essentially this, what you should, the most obvious thing to do is just Y quotient by S1 to cancel out all this stacky perspective of intersection basically. So this checking that the morphism of this two 3D mirror object is the same statement about the Telemann conjecture. These are understanding the. So if this is the case, that's like a Hori-Rafa case. As I mentioned, in general, there is certain further correction for this to hold true. Okay, so that was the 3D perspective of this statement. Okay, now how about the non-abelian case? G is not G. That. So what is this space? So we just mentioned that if you are in the abelian case, this is just a cotangent bundle of T check C, okay? And this BFM space for the G check, what should that be? Okay, so it turned out that first of all, these two are birational. So this turn out is a birational to this space or up to the wild group action as usual. But the birational is everything, basically. Everything is contained in the place which is not the same. So let me just show you the simplest case. So for example, G equal to SO3. Okay. So what's the wild group? So this is the wild group of G. Okay, it's the same as the wild group of G check anyway. So in this case, the wild group is Z2. Okay, and this space is the following. This is you look at this space quotient by Z2. Okay, so you start with this one. This is C star and cross C. Okay, C star cross C. Okay, and then you look at 1 and -1 here. Okay, you blow up that. You blow up 1 and -1. We start from this space, blow up the center, and then remove this whole, remove the zero sections. That was the space in this case. Okay, so it's not surjective or injective. It's just it's bigger but also smaller. Okay, you blow it up, and then remove the zero sections. Okay, so you get a similar description of all the BFM space for other G. So what we need to prove is the following. So let's say if you have a SO3 acting on Y, and then you look at the Cartan subgroup, which is S1, of course, in this case. Okay, and then Y check is just S1 invariance Lagrangian. Okay, the S1 invariant, and so on. Okay, and then you get W check. Okay, so that would define U and then pi. Okay, And then that will define you something in here. So first C star, and then C. And then map to C, you look like this one. Y map to C, and then you also have a potential function here. But then, as I mentioned, you have to use this Lagrangian, holomorphic Lagrangian correspondence to move it to a Lagrangian. So then Lagrangian might look like this, something. Maybe multi-layer. I mean, don't have to be, could be like this. Okay. So what you need, how do you know that it descends down there? Meaning that it has to have the following property, that you need to argue that in this example, that if these sections start to hit this fiber, the sections that you get, well, from this you get a Lagrangian, you get a complex Lagrangian. The section, multi-section, when you hit this, it has to hit at this point transversely. So therefore, then it will hit here, because it cannot hit any other point here. Yeah, whenever you hit, it has to hit this here transversely. Okay. Well, sorry. When you hit the zero section, when you hit the zero sections, okay. So you cannot not on the fiber. If you hit the zero section, it cannot hit like this. Okay. When you hit the zero section, it can only hit at the center of the group G, and then it has to hit transversely here. Okay. That's what you need to prove. That's what we prove. Yeah. Assume this normalization of that. Yeah. So then we prove that if you get this normalization of floor homology, that is true for all G. Yeah. That was the first film. Yeah. Yeah. So in the abelian case, the BFM space is just this one. That's why we are looking at C star all the time, right? But in the non-abelian case, then there's a subtle difference between this and that space. And then we argue that it exactly handle that. Well, I haven't been there yet. That is the next question. Yes, yes. So we first have to show that this really defines you an object in the BFM, in the Coulomb branch. Yeah, and then you have to do the quotient. That we are not there yet. Yeah, yeah. Also, I should say that there's also co-string analog for this. The complex Lagrangian was in abelian case. In a okay, that it just define the complex Lagrangians that was studied by Paul Marihano, maybe, and Mac, and talk about the thing on the symplectic space and the quotients. This kind of reduction statement in the abelian case, and final example. There's a close analog with the claimed by Paul Marihano and Telemant. Yeah, recently. Yeah. So we are doing it from SYZ perspective, and then also we also describe the differences that you really have to correct it when it's not final. Yeah. Yes. Yes, 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 yeah, yeah, yeah. Thank you.